This is 20 millimeters. Okay. So the flange now, the equation for the flange has a limit. Okay. The limit is 0.015, your y, and then it will go up to 0.035. I'll try to write visually, okay? Now, why do we set that limit? Okay, because if you look at the limit, an interesting thing to see is the thickness is equal to what? 0.16 meters. So we know the dimension from here to here is equal to what? 0.16 meters. Yes. It's because Y bar, the geometric centroid is 35 millimeters from the top. I've given that. Okay, I want to go and find the centroid, the waste of your time and my time. Okay, right? So the limit is based on a constant what? Thickness. I repeat again, the limit is based on what? Constant thickness. And it's also based on the part of the structure that we are looking at, and we are looking at the what? At the flange. So I'll write down here, note the limit is based on constant what? Thickness, right? It cannot go lower. If I go lower, then we go into the what? The web, and the web section, the thickness what? Changes. Yes or no? So we have to formulate based on the limits is based on the thickness of the beam. Okay. So now this is where it's straightforward now. Okay. So we know this is our ZZ axis. So our first moment of area about our ZZ axis will be equal to area multiplied by Y bar. So this is equal to width multiplied by depth multiplied by Y bar. Okay. So now, the next thing that we have to take note, the axis is what? ZZ. So we know you have to draw this down. What we're interested in the shear is all about the what? ZZ axis. When there's an exit and when there's an axis, this is equal to our what? Width, and this is equal to our what? Depth. It's interesting, isn't it? We apply this in buckling, we apply this in bending moment, we apply the same thing in what? Shearing. We clear? Okay. So from here, our width is equal to what? Our width is a constant, is equal to 0.16. Our depth is equal to 0.035 minus y. And then the Y bar is equal to 0.035 plus Y, and then we multiply by half. So this over here, this is our width. This over here, define our depth. This over here, define our Y bar. Seen this before? Yeah. Wednesday lecture. If you go to Wednesday lecture, right? If we go to Wednesday lecture, can you all remember this? What do we have? C minus y, C plus y multiplied by half. Okay, so I'll do you a favor. Okay, I'll come here. I'll copy, and then I'll come over here. Okay, and I will paste. And then when you see, you don't feel that there's anything new. Yes or no? It's the exact same thing. Okay, so from here, only now we have numbers. Okay. So from here, we can write out this will be equal to calculator. So 0.16 multiplied by 0.5 multiplied by 0.35 squared is equal to 98 times 10 to the power minus 6. Okay, and then 0.16 times by 0.5, we have 80 times 10 to the power minus 3 y squared. Okay. So from here, we can find out our shear xy as a function of y. So we are going to apply Vy over Izz, Qz divided by T. We know this, we know this, we know this, we know this, we are good to go. Okay. So this will be equal to 90 times 10 to the power 3 multiplied by 98 times 10 to the power minus 6 minus by 80 times 10 to the power minus 3 y squared. Okay. And then, oh, the squared look horrible. Y squared. And then the whole thing divided by the second moment of A, which is equal to 5.813 times 10 to the power minus 6. And then based on the thickness is equal to 0.16. Okay. So from here, 90 power 3 times by 98 power minus 6 divided by 5.813 power minus 6 divided by 0.16 is equal to 9.483 times 10 to the power 6. Okay, minus 90 power 3 divided by 5.813 power minus 6 divided by 0.16 times by 80 power minus 3. 7.741 times 10 to the power 9 y squared. How do you know that this is right? Yes, sir. What endpoint? What's the value? Yeah. Remember what I told you? One of the rules is what? The analysis starts at where? Y next. Yes or no? So if you plug this in, okay, if you plug this in, when you use y is equal to 0.035, the shear xy at y, hey, this thing must be equal to 0. So I'm going to do that. Can you all do that also? 9.483 power 6 minus by 7.741 power 9 times by 0.035 squared. And the answer, I get 275. Come on, it's very low. Okay, 275, what's the unit? Pascal. What is 275 Newton? Anyone? Oh, it's not liter, but it's very insignificant, okay? It's about 9 kilograms, okay? It's not, okay? So it's small, so it's approximately equal to what? 0. This is because of some of our rounding, okay? Now, the next thing that we would like to calculate, I like to determine the shear force resistance, okay, by the flange. Okay, the shear force resistance by the flange. Flange, not French. We only have 30 kilonewton, 90 kilonewton of force coming down. How much is taken by the flange? How much is taken by the flange? So to do that, okay, you cannot to do that you cannot do what? Stress is equal to what? Force divided by what? Area. Yes or no? Why we cannot? Question for you guys. Why we cannot use shear stress is equal to force divided by area? Anyone? Why we cannot use that? How come when it's under axial loading, you can use force divided by area? For this case, we can't. What is the difference? Yes. No. The problem is math. Why? Okay, when we calculate axial load, right? When we calculate axial load, it's our fault, okay? When we calculate axial load, right? This is P, and the stress on this is equal stress divided by P over A. Right? We make an assumption. What assumption did we make? Okay? It's okay when the area is constant, but what's the problem with that expression over there? What we assume is over here, this, so if this is our normal stress, right? We assume that this is our average stress is equal to P over A. Yes or no? We assume it P over A. In real life, how does this look like? In real life, the distribution will look like this. Okay, but we assume P over A. What we are formulating over there, is it an average value? It's not. What we are formulating over there, if we look at the, why am I using the board? What we are formulating over here, why did I use the board? What we are formulating over here, we are not calculating a constant. So if this is our shear, hey, what is happening? If this is our shear stress, this is our Y. So this over here, this is 0.015, 0.035. We are formulating the what? We are formulating the distribution. That's why we cannot say why not use that and divide by area with a thunderbird cargo. No. Okay. So to do this, all we need to do, okay, is this. So to find the shear force resistance F, okay, all we need to do is we just integrate shear xy as a function of y dA. That's it. Okay, that is the purpose of deriving the distribution equation. Are we clear? Or not? There's no purpose. Or you can sketch this. Okay, you can sketch it, but whatever. Okay. So from here, we are going to integrate, and we know that the lower bound is 0.015. The upper bound is 0.035. The shear stress is equal to 9.483 times by 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared. Now, the change in cross-sectional area, right, is dependent on the what? So is this cross-sectional area that we are talking about, right? The green one that I've shaded. So we know that the what? That the width is constant, dy is the only thing that is changing. Okay. So from here, we write down, we integrate this, okay, 9.483 times, come on, 9.483 times 10 to the power 6y minus by 7.741 times 10 to the power 9 y cubed divided by 3, and then we have 0.035 and then 0.015, and then we are going to multiply the whole thing by 0.16. Okay, so let me tidy this up. So this will be equal to 1.517